Hey there, Chem 20s. As promised, here's just a short little video that kind of captures some things that we talked about during our Google Meet today. And just to remind you guys that this material that we're doing now in Chem 20 is important not only for you as a learner, but for going forward to Chem 30. The stuff that we're doing in bonding is important for setting you up next year in Chem 30 for organic chemistry. And the stuff that I'll be talking about later on solutions is going to be important for you in Chem 30 for acids and bases, and also to some extent for the redox unit. So we're setting ourselves up here. We're getting a baseline, and we're getting the ground knowledge, the foundation that we need moving forward. So one of the questions on the formative last week was asking about the polar molecule water. And so when you draw the water molecule out, you'll notice it's V-shaped. And of course, any V-shaped molecule by its nature is a polar molecule. It's not symmetrical. But looking at the electronegativity difference between the oxygen and the hydrogen atoms, we have ourselves a dipole here. We have a net dipole, which is going to mean that we have these polar bonds. And this means that all the electrons are hanging out around the oxygen atom. So since electrons are negative, that means that the oxygen becomes the negative end of the molecule. So a lot of students answered that one incorrectly. They said it becomes the positive end. That doesn't really make sense, right? You've got negative electrons, so that's the negative end of the molecule. The hydrogens don't have the negatives, so they're partially positive. And of course, that's what sets up that attraction, like a hydrogen bond between the hydrogen of one atom, of one water molecule and the oxygen of another. A couple other concepts just to clarify with you guys. Again, when you're looking at your bonding continuum, you should have this memorized, right? You should know these numbers now. What is nonpolar, polar, and ionic? And I think a misconception is that this, by saying that it's ionic, it doesn't necessarily mean that there's a metal and a non-metal in that compound. A polar covalent compound can act like or behave like an ionic compound based on its electronegativity difference. So again, when you're evaluating compounds, you draw them out, you look at them, you look at electronegativity differences, find out where do they fall along the continuum. Are they polar or non-polar? This question was done wrong by a lot of students. And I think, again, maybe the misunderstanding is here's a non-metal, yet it acts like an ionic compound because the electronegativity difference is so large. 1.8 is in this ionic range, and therefore it acts like an ionic compound, even though it is molecular. Okay, so that can happen. You can have molecular compounds acting like ionic ones. Another question that a lot of students struggled with was the question about the group 16 compounds. And the common answer that was incorrect is students picked D. And I think students picked this because they looked at the London forces. They counted up the total number of electrons and saw, yikes, that guy's got 54 electrons. That's a huge amount of intermolecular forces. He must have the highest boiling point. Wrong. It is the strongest intermolecular forces that are more important in determining the boiling point than a weak force like London. Also, it is the number of forces that you have. So a water molecule, even though it had the lowest number of electrons and the lowest London forces, it has a dipole. Why? Because it's a polar molecule. We just talked about that. And it also has a hydrogen bond, right? There's this covalent bond between O and H that causes there to be an attraction between another water molecule. This is the hydrogen bond that we're talking about, this intermolecular force between two water molecules. So because it's got these really strong forces, it's got more intermolecular forces, means its boiling point will be higher because now you have to overcome those forces. You have to put more temperature in to boil that compound. So A would have been the correct answer there. So again, boiling point, solubility, melting point, all these physical properties are due to intermolecular forces. Remember, intermolecular is between two or more molecules, not intramolecular, not inside of a molecule, but between molecules. Okay, I'm going to zoom into this one a little bit here. So there was one question where you had to rank boiling points from the lowest to the highest. Anytime you are given a question like this, you must draw it out, right? You got to draw it out, and then you got to assess what are the different intermolecular forces. Does it have London? Does it have dipole? Does it have hydrogen bonding? Again, London is the total number of electrons. So a lot of you probably were like, wow, bromine has 70 electrons. But you know what? It is not going to have the highest force, because here's a guy who has the two strongest forces. Ammonia is only 10 electrons, but it has more dipole because it's polar, and it has this really super ultra strong hydrogen bond. So it's actually going to have the highest boiling point because it has more forces and more stronger forces. So helium obviously only has London, so he's the lowest. Ethane, second lowest, and now we're talking bromine because he has 70 electrons. Okay, what else did we need to talk about? Okay, again, when you're doing intermolecular forces, I've said this a couple times already, draw out your molecules. Decide, do they have London? Do they have London and dipole? Are they polar or not? Do they also have hydrogen bonding? So for this example, there was a numerical response question, and I believe the answer was 3, 1, 2, 3. You had to draw them out, and you've got to go through each and every one of these and decide, how many electrons does it have? Is it polar or not? Does it have hydrogen bonding or not? The more forces it has, that's responsible for higher boiling point, solubility, etc. Okay, so moving on from there, talking a bit about what is in our this week coming up. We're starting with our solutions unit, and you have a note guide on introduction to solutions. So you need to know about a solute and a solvent. So many of you have made Kool-Aid, and you take the Kool-Aid packet and you add it into water. So the Kool-Aid is going to be the solute, what you are dissolving, and then the solvent is going to be the water that you add, and then you make up a solution of Kool-Aid. So we also learn about, and this goes back to Science 10, we talked about conductivity meter, and the little light would glow if it was an electrolyte solution. And an electrolyte solution is one that has ions. Ions are able to conduct electricity, and therefore they would make the conductivity meter glow. Whereas a non-electrolyte is something that is molecular, would have no ions in it, and it would not make the conductivity meter glow. So acidic, basic, neutral, you guys know this from Science 10, even junior high science. Acids are going to turn litmus red. Why? What makes an acid an acid? Well, the reason an acid is because of hydrogen ions. Bases, you know, are going to go blue. Why? Because of hydroxide, right? The reason why is they're ionic compounds that have a hydroxide. Neutral compounds are going to not change litmus, right? Red stays red, blue stays blue. How come? Because there is no hydrogen and there's no hydroxide. All right, so we know the reasons for this, and we can test solutions for this. We can test solutions for being qualitative, and so meaning that they have some sort of characteristic. Quantitative is a measurement of how much there is of something. So like maybe I'm going to take the mass and I weigh it out. Oh, it's 5.00 grams. Qualitative might tell me, oh, well, my solution is blue in color. So it tells me that I have maybe a copper ion present, but it doesn't tell me how much. So qualitative just tells you something about a solution, but it doesn't quantify it, doesn't tell you how much. Quantitative will tell you how much there is. So you read through and learn about some qualitative and quantitative tests. And then you'll also read about concentration, which is just a ratio. Solute, the solid, the thing that gets dissolved, like the Kool-Aid mix, and divided by the solution. Okay, so it's a ratio, and you will have to do some calculations. And the units that we use for concentration is moles per liter. We call that the amount or molar concentration. So concentration in moles per liter, chemical amount in moles, volume in liters, and being able to convert. And you guys know how to do this already. You've done stoic. This is just like gravimetric stoic, going from grams to moles, using molar mass as a conversion factor. We're leading up to eventually doing solution stoic, right? So eventually we're going to get there. You guys will do some practice questions, calculating. Maybe you're given moles and you have to find volume and you have concentration, or maybe you're given volume and moles and you have to find concentration. Anyways, you can read through that note guide, and if you have any questions, you will of course email me and let me know. There's going to be 2 assessments this week. One is a formative on bonding. One is a solutions formative, and the second is a summative on bonding. Okay, so again, if you have any questions, just let me know. Take care. Send me an email when you need to, and we'll talk to you later.